Okay, here's a look at our third review. This one's on stoichiometry. We'll start with number 1, and it's giving you an equation here. It says iron chloride plus sodium hydroxide produces iron hydroxide and sodium chloride. And it's asking us if the equation is balanced. So, easiest way to do this is to just count. Okay, we have our arrow. Separate the products from the reactants, and we'll count the atoms that are on the left side compared to the atoms that are on the right side. So let's take a look at it. If I've got in my first reactant here, I've got iron chloride, which means I've got iron and chlorine. So how many irons do I see? I only see 1, and I count 3 chlorines. So I've got 1 iron and 3 chlorines. My next reactant, I've got a sodium, I've got an oxygen, and I've got a hydrogen. So let's see here. The 3, remember, the coefficient distributes to everything. So it distributes to the sodium, the oxygen, and the hydrogen. So with that being said, that means I've got 3 sodiums, 3 oxygens, and 3 hydrogens. Let's look on the right and see if it's balanced. Got iron, oxygen, and hydrogen in my first product. The 3 only distributes to what's inside the parentheses. So I've got 1 iron. I've got 3 oxygens and 3 hydrogens. In my last product, I've got a coefficient that distributes to the sodium and the chlorine. So sodium's got 3, and chlorine's also got 3. So when I compare, I've got 1 iron on the left, 1 iron on the right, 3 chlorines on the left, 3 chlorines on the right, 3 sodiums on the left, 3 sodiums on the right, 3 oxygens, 3 oxygens, 3 hydrogens, 3 hydrogens. So the equation is asking you, or the question is asking you, is this balance? Is this reaction balanced? The answer is yes. So what will the coefficients be? Coefficients are the big numbers. So there's no number here, so it's implied it's a 1. I've got a 3, another implied 1, and a 3. So my coefficients are 1, 3, 1, 3. So besides using a balanced equation, what do the coefficients represent? Coefficients are the number of moles or the molecules in the reaction. So what is stoichiometry? Stoichiometry is the use of mole ratios from a balanced equation. We've got to make sure that the atoms on the left equal the atoms on the right. That allows us to calculate the amounts of reactants or products. So it doesn't just predict the reactants, it doesn't just predict the products, it predicts both. So moving on, it says use the balanced reaction below to give us the mole ratios. So the mole ratios are found by looking simply at our coefficients. So I see a coefficient here, a coefficient here, and a coefficient here. Now even though this one's not written, this is actually a 1. So my coefficients are 2, 1, 2. So the ratio of hydrogen to oxygen. Well, looking up here, I've got 2 hydrogens, or a coefficient of 2, and for my oxygen, I've got a coefficient of 1. So my ratio is 2 to 1. In water, water has a coefficient of 2, and oxygen has a coefficient of 1. So the coefficient of water to oxygen would be 2 to 1. Water, H2O, again has a coefficient of 2. Hydrogen has a coefficient of 2. So the ratio would be 2 to 2, but I can reduce these by a factor of 2, which leads me to 1 to 1. All right, some conversion factors. Are they correct or incorrect? So A says moles of carbon dioxide to moles of water. I can go from moles of one substance to moles of a different substance if I know the mole ratio, so this is a correct conversion. I cannot, however, go from grams of one substance to grams of a different substance, so this is incorrect. We don't have a grams to grams conversion. In C, I've got moles of oxygen over grams of oxygen. I can go from moles to grams as long as I stay within the same substance. So here I'm looking at oxygen and oxygen, so they are the same, so this is a valid conversion. And in D, it says grams of oxygen to moles of hydrogen. These are 2 different substances, therefore this one is not a proper conversion. All right, on the back side. So on the back side, we're going to use the coefficients, and we're going to convert from moles of one substance to moles of a second substance. So in number 7 it says, how many moles of oxygen gas react when 12.5 moles of copper to oxide are produced? So identify the information that is given to you. So I've got 12.5 moles of copper to oxide, and I want to figure out how many moles of oxygen that is. So this is my given information. This is unknown. So I'm going to write what's given to me first, which is 12.5 moles of CuO. And I'm going to rewrite my units, moles of CuO. And I want to convert from moles of CuO to moles of O2. So now I need to look at my mole ratios. So I'm comparing oxygen to copper oxide. So look at the coefficients. Coefficient here, an implied coefficient there, and a coefficient here. So remember the implied coefficient is a 1. So I've got 2 moles of oxygen, 1 mole of oxygen gas and 2 moles of copper oxide. So a 1 goes here, a 2 goes here because that's my mole ratio. So the math is 12.5 times 1, which is just 12.5, divided by 2, which gives me 6.25 moles, making my answer choice A. All right, looking at the next one. Determine the moles of copper to oxide produced if 4.25 moles of copper react with oxygen. So the information that is given to me, and I'm going to go from moles of copper to moles of copper to oxide. So I'm going to start with the information that's given, which is 4.25 moles of copper. So I'm going to bring down my units, moles of copper. And I want to convert 2 moles of copper to oxide, which is CuO. So the ratio of copper to oxide, I've got a coefficient of 2 for copper and a coefficient of 2 for copper to oxide. So the ratio is 2 to 2. So we're going to write that in here as a 2 to 2. So 4.25 times 2 divided by 2 is just 4.25. So essentially these 2's cancel out, and I'm left with 4.25 as my answer, which is answer choice A again. Okay, now we're looking at moles to grams. So here I've got 2 moles of aluminum oxide. I've got 4 moles of aluminum and 3 moles of oxygen gas. The question's asking me how many moles of Al2O3 aluminum oxide decompose when 4.5 grams of oxygen are formed. So this is my given information, and this is unknown. So I'm going to start with what's given, 4.5 grams of O2. And then I'm going to rewrite my units down here, grams of O2. Now the T-chart is drawn for you, so it gives you the hint that there is an additional step. Now, according to the conversion that we did on the front side, I cannot go from grams of one substance to grams or moles of something different. So I have to go from grams of one substance to moles of the same substance. Okay, so this is where my molar mass comes into play. So I know that, according to my molar mass, 1 mole of oxygen is equal to the molar mass of 2 oxygen atoms, which is 15.999 times 2, which gives me 31.998. And I found this on the periodic table. These are the decimal numbers, the molar mass. So when I continue on, I'm going to bring down my unit, moles of O2. Now I can go from moles of O2 to moles of aluminum oxide. And that's where my ratio comes into play. I've got 3 moles of oxygen gas and 2 moles of aluminum oxide, so the ratio is 3 to 2. So the coefficient for oxygen is 3, the coefficient for aluminum oxide is 2. So the math becomes 4.5 times 1 times 2, all divided by 31.998 times 3. When you type that into the calculator, you should get 0.0938. It's best to use parentheses for your numerator and denominator so that you don't get confused, so that your calculator knows exactly what you're trying to do. If you don't get 0.0938, try it again. Parentheses might be your issue. Number 10. How many grams of aluminum are produced when 3.75 moles of O2 are produced? So here's my given information. And I'm trying to find grams of aluminum. So I'm going to start with what's given. 3.75 moles of O2. And then I rewrite moles of O2. Now, again, I cannot go from moles of one substance to grams of something different, but I can go from moles of one substance to moles of something different. Okay, so moles to moles, that's a mole ratio, and I find that in my coefficients. So if I'm comparing oxygen to aluminum, the coefficient for oxygen is 3. The coefficient for aluminum is 4, so the ratio is 3 to 4. So those are the numbers that I write in my T-chart. So the coefficient for oxygen was 3, the coefficient for aluminum is 4, and I continue on with my conversion. So I'm going to bring down my units, moles of aluminum. And now I can go from moles of aluminum to grams of aluminum. So this is molar mass. So 1 mole is equal to, according to the periodic table, aluminum has a molar mass of 26.982 grams. So remember, this is molar mass. This is molar mass, and this was your mole ratio. Okay, so according to the calculations, you got 3.75 times 4 times 26.982, all divided by 3 times 1, which is just 3. And according to the calculation, I should get an answer of 134.91 grams, which rounds up to 135. Okay, and lastly on the right, the limiting reactant. So limiting reactant causes the reaction to stop or to run out. So in this example, I've got 3 burger patties, 4 buns, 1, 2, 3, 4, 5, 6 slices of cheese, and 1, 2, 3, 4, 5, 6, 7 tomatoes. Okay, so if each burger has 1 slice of cheese, 1 bun, and 2 tomatoes. So that if I start crossing those out, I get 1 burger equals 1 bun, 1 slice of cheese, 2 tomatoes. 1 patty, 1 bun, 1 slice of cheese, 2 tomatoes. 1 patty, 1 bun, slice of cheese, 2 tomatoes. So everything that's left over is what I consider an excess. So I've got a bun here, 3 slices of cheese, and 1 tomato, which is what I see over here. These are known as my excess reactants. So the limiting reactant is what runs out first. So in this case, the meat patties ran out first. So without the meat patties, I can't make a hamburger. So the excess ingredients here were the buns, tomatoes, and the cheese. Those were my extra ingredients. Those are my excess reactants. I could do the same thing with a reaction. If I've got X plus 2Y produces Z, the mole ratio of X to Y. So it's implied that the coefficient for X is a 1, for Y it's a 2, and for Z it's a 1. So the ratio of X to Y is 1 to 2. Okay, so if I want to use the reaction up above in box 1, figure out what the limiting reactant is. So let's look over here to the right. If the reaction is set up to follow the ratio of 1 to 2, so for every 1x I have to cross out 2 y's. So 1x crosses out 2 y's. 1x crosses out 2 y's. And I've got another x, but I don't have any more y's. So what ran out first? The y's ran out first. So if the y's run out first, then y's are my limiting reactants. Let's try the same thing in box 2. So again, for every 1x, I cross out 2 y's. So here's 1x and 2 y's. 1x, 2 y's. 1x, 2 y's. So I don't have any more x's, I don't have any more y's. So in this case, they were both consumed equally. And the last part down here at the bottom. It says calculating percent yield. So in this lab experiment, chemical reaction produces 52.5 grams of carbon dioxide. The reaction should have yielded 53 grams of carbon dioxide. Calculate the percent yield. So the actual yield, what the experiment actually produced, was 52.5 grams. What it should have yielded, the theoretical yield, is 53.0 grams. That's what the reaction should have produced. So to calculate percent yield is your percent yield equals the actual yield, and I'll abbreviate that AY, actual yield, divided by theoretical yield times 100. Anytime we convert to a percent, we have to times or multiply by 100. So actual yield, this is AY. Theoretical yield, this is TY. So when I plug this into my equation, I get 52.5 divided by 53, my theoretical yield. Divide those first, and then multiply those by 100. So when you multiply it by 100, you should get 99.1%.